To everybody, it's not exactly the time I was expecting to give my talk. I would like to thank Francesco for this organization of this nice conference in so nice places. It is really to have outside of our hall now this beautiful view with this beautiful statue on these stones which are so old. It's a rather beautiful experience. Now, I want to speak about the large plastic deformation of crystals at nano and micro scales, and I would like to acknowledge my co-workers, Jalal Smirni and Salman from my laboratory, which is...
You should use the microphone.
You cannot hear me. Okay. Okay.
No. We will give you the mic.
Okay. Okay. Now it's better?
Yes.
Okay. Thank you. The outline of my talk, which it is rather ambitious, maybe I will not be able to do it everything. To just speak about at the beginning on the Eulerian approach of large deformation of crystal plasticity, to introduce some models. After that, I want to speak about lattice orientation attractors, about dislocation density attractors, and if I have time, also about intragranular void evolution. Now, let's start with this model of, it is a continuum mechanics modeling of crystals, which is presented here a little bit. We need to have a number of slip systems. A slip system is related to a slip direction and to a normal of the slip. You can see here, we have one normal and three slip systems. And on each slip system, we have a viscoplastic shear rate. And with these two vectors, the slip direction and normal to the slip, we construct this symmetric part and anti-symmetric part of the tensorial product. Now, we are speaking about very large deformation, and if we compare this deformation, which will be around of 50%, 100%, very, very big deformation. Even sometimes you don't need to have an overall large deformation, but in shear bands, in some places where we are interested in, the large deformation are present, and they are all around of 50%, 100 to 100%. And the elastic components are always very small. Always it is related to around 1% for this type of materials. That is why we can, let's say, neglect them and to write the deformation gradient as the product between the plastic deformation and a rotation. That means that in all of that, this description, we don't have any elasticity. It is also will simplify the model, and the problem when you have elastoplastic problems is that plasticity it's more simple to express in Eulerian coordinates, and the elasticity is more simple to express in Lagrangian coordinates. And when you have both, you have a little problem. But here, for large plastic deformation, we can suppose that we neglect this elastic part, and we have more simple model. And what we have here to see that if V is, for instance, the Eulerian velocity field, and you have the gradient of the velocity field, which is composed in the symmetric part, the anti-symmetric part, And the symmetric part, it is related to the slip rates by this decomposition, you see? While the antisymmetric part give you a differential equation for the rotation field. Now, how we have to do this decomposition of the strain rate to the slip systems. This is done on the viscoplastic or rigid plastic law, which relate each slip rate with the resolved shear stress. Resolved shear stress is the expression of the Cauchy stress on this slip system. Here we have, let's see, this is a Schmidt law, which is rigid plastic, and two types of regularization are here: the power law, the Norton law, and the Pergina or the overstress law, which are two kinds of regularization. And in this case, we can introduce this dissipation energy, and the slip rates are the minimum of this energy obtained by minimization of this energy with the constraints of the decomposition related to the strain rate. That means this is if we have the stresses, we can find directly the slip rates, but we have the strains, you have the strain rates, we have to minimize this function with this linear affine, let's say, constraint. What we have to add is another parameter, which is the dislocation density, which will give you the evolution of the yield limit of each slip system. For instance, you have here this dislocation density, which is something which it's a parameter in continuum mechanics, but it can be also, let's say, it can be measured sometimes. It's not so simple to measure it, but we can do it. And the shear yield stress is expressed like that, for instance. And we have another equation for the evolution of the dislocation density, which have two parts, let's say, the multiplication part and the annihilation part. It means at the end of the day, we have a model which is constructed on the decomposition of the strain rate on the slip systems. On each slip systems, we have an energy which is related to the shear yield stress, and this shear yield stress can be constant or not. If otherwise, it depends on this dislocation density, which is one of the parameters which is used. Now, as you see, it's too complicated. There are too many equations, too many things, and not because the nature is very complicated, but we are not able every time to understand. That is why we have to simplify the model such that we can understand something. And one way to simplify is to consider a 2D system where we have only 3 slip systems, like here, you can see, and the lattice have this angle phi between B1 and B3 and B1 and B2, and all the lattice is now the orientation of lattice is given by this angle theta on x1. It means in this case there are two situations when we can do that. One is when we have the projection on FCC crystal on a plane. Let's see, it's rather complicated. You have to combine 2 slip systems and such that we have a planar deformation. and three pairs of slip systems, and after the other 6 have to be inactive. Or you have the hexagonal crystal, and we have here, this is more simple. And for the first case, we gave the angle phi, it's around 54 degrees, and this one is 60 degrees. What are the main simplification? That now, if we have this equation, all the rotation equation is now written in a very simple way, as a differential equation for the angle, where we can observe here the presence of the slip rates. Now, the other main simplification that we can have a formula. We don't have to minimize this energy with this constraint at each time step, at each point in the we have a formula which gives you directly the slip rates as function of the angle theta in the slip rate decomposition. This is there are two main simplification. And now I will want to speak about lattice orientation attractors in this velocity gradient driven processes. That means in this case that we fix the strain rate. The strain rate, not the strain, it's more complicated because it's not only the strain rate which I used. Now it is also important to have the rotation of the lattice. That means we have to fix the gradient of the velocity. Let's say it's fixed, it's given. And this is always decomposed in the symmetric part and anti-symmetric part. And we can choose that the of the strain of deformation are the x1, x2, and then we can write the deformation tensor as like a diagonal, let's say. And we have only two small parameters, d and omega, which omega is the rotation rate. And the equation now, it's written of the lattice orientation is written like that. It is a differential equation. Where this function g of theta, here it's theta between 0 and pi. And here you have two expressions of g for the FCC crystal and for the hexagonal one. That are almost the same, and it is always between 1 and -1. And if we want now to see what are the stationary orientations, the orientation which are not moving, let's say, they are not evolution, no evolution on the lattice orientation, then we have to solve this equation. And if a stationary solution has the derivative negative, then it's an attractor. That means we have here, I can see you, there are three situations. The situation when you have here the G2 omega over d that is between -1 and 1, and then you have 6, let's see, 6, 1, 2, 3, 4, 5, 6 stationary solution, but only 3 of them are attractors. And we can see here, you have the basin of attraction of this attractor. So that means if the initial orientation is here, then we'll go on this direction. If it is here, we'll go on this direction, and so on. You have here 3 basin of attractions. Now we can see that, and let me finish. If we have in this situation, then we have it's an attractor from the left and not from the right. It's unstable. And here we have no stationary, no attraction. And here I have plotted the evolution. The time is here, evolution of different orientation on the circle with, in time. And we can see here the attractors. There are 6 attractors, in reality only 3 because there are some symmetries. Here you have the attractors on the left and not on the right. And here we have no attractors at all. It is the crystal, the lattice have a too big rotation. Now the problem is I have some movies, but they are there. But I want to show you some movies. There is another. I have some. Okay, I will speak about. There are some movies in another folder. Can you open that? It is a folder of anime. Another folder, it is a presentation, PowerPoint, presentation 1, a PowerPoint, if it is not, presentation. Okay, now it's working. Can you put it in? Okay. What can you see here is 16 grains subjected to a velocity boundary condition. The velocity boundary condition, which is related to fixed, let's say, strain velocity gradient, but we can impose that only on the boundary. And on the top, you have the evolution of the grains, the orientation of the grains, and on the bottom you have the prediction with the attractors. And you can see at the end the difference is not so big between what the computer have done after 20 hours of computing and what we have, the prediction we have with the attractors. It cannot be exactly like that because as a matter of fact we have supposed in all this theory that the strain rate is constant everywhere, which is not exactly what happened. We can impose the boundary condition, but the crystal after that have a different behavior and they have to manage the different orientation of the grains between them. The next one. Now here, I don't know, you have to have here a movie also if you, now here you have the difference. This is a difference between the attractors and the orientation. And you can see that at the end, the only 2 grains were not well estimated. All of them rather good. And this is rather complicated. And here you have the L2 norm of the difference between the attractor and the orientation. And you can see that every time this is growing down, and now is stopping because at least 2 grains was not very well solved, but all the other was rather good. Now, can we come back now to the? Can we come back to the presentation? Yes, this one. Now, what I want now to speak about a slip strain driven problem in and attractors in this case, but I really don't have time. I will go directly to the point, to have the pitch of the problem. You always, it's the same idea. You fix something, we do a stability analysis for some evolution equation, and we try to understand what happened. And in this case, for instance, we find dislocation density attractor, or let's say here you have this, such that we deal with a hardening process if the initial dislocation is less on this value. We have a softening process if it is larger than this value, and you have a plateau if the initial dislocation is around this saturation point. And why was, and we have something like that here. You have different evolution, and you have, this is the saturation, and here we have the evolution of the EL limit, softening and hardening. What I wanted to point out that in all this analysis, you have to obtain something interesting, you have to have very large deformation. Here you can see that the deformation, it's the dislocation is near the value of attractor for starting with 50%. And it was always the same in this case here. You can see here the deformation, the attractors is around here 40%. 40%, all this analysis is valid after 50% of deformation. On small deformation, we obtain nothing. Let's see, it's specific for large deformation. And what it is a point here, it is related to an experiment which have been done in the beginning of 20 about, you see, it is very in fashion now to have these micro pillars. They are crystals which are gross, and after that they are doing a hole around, and they found these pillars, and they press these pillars like that, here, and here, and they obtain that the same material for when it has 1 micron, it have a shear band, and when you have 10 microns, it have no shear bands almost at all. That means it is a scale effect, and there are people which try to explain that with some models which have which are related to the size. But this model is not related to the size, but is related to the dislocation. And what can you see here? That the dislocation, initial dislocation, is larger for small sample diameter. Here you have the experimental ones. This is a theoretical numerical computations. And we can see here the initial dislocation density. It's larger than it's exactly what we can find on this stability analysis. That means when you have a smaller specimen, you have a softening process, and when you have a larger specimen, you have a hardening process. When you have a softening process, then you can expect to have the shear bands. When you have a hardening process, the shear bands disappear. That is why here I have a movie which is not working. Let's see, here is the results of the computation. I will show you, just tell you what it is. Here is the three pillars, and this is a numerical computation with the model. And we can see here that after the compression, this will obtain here a shear band, and this one, the other one, not at all. That it's not working on this computer, the movie. Only 1 minute. 1 minute just to tell you about how this model can be used to see what happened in the voids in the crystal. Here you have these points here are intergravitable cavities. They are also intergranular cavities, and we wanted to see what happened on this case. There are a lot of very nice work about the onset. The onset that means small deformations, the real beginning of the. But this all this situation can explain what happened at the beginning, what are the shear bands, what happened with orientation and so on. But it's very difficult to see what happened after a large deformation. You can see here, even if the volume is very a small deformation of the volume, the deformation of the void is very large. Here, the deformation around the void is very large. And here you have the result of this model, which cover the initial onset, and little by little you obtain this form, which is an hexagonal form, which is very close to what we see experimentally. You can see here. This is the theoretical part and numerical pattern, and here we have other examples when we have a void in a pillar which is in traction, and what happened with the shear bands and so on. And we can stop here. Thank you very much.